Hello everyone, I'm Kyle from Penn State. Today I will introduce OmniScan, a benchmark that evaluates whether multimodal models can understand real PCB schematics and convert them into structured circuit graphs. Schematics appear in EDA tools, datasheets, and textbooks. They combine symbols, test wires, and spatial conventions. To support simulation and PCB design, these images must be converted into machine-readable netlists. This conversion is challenging because circuit symbols and drawing styles vary widely. Connections may include wire crossings, labels, buses, hierarchy, and hidden pins. The model must also translate geometric layout into electrical topology. Therefore, this is not just OCR. It requires both visual recognition and connectivity reconstruction. Existing benchmarks mostly contain simplified circuits and a small number of symbol categories. Their supervised vision pipelines can detect a component but provide limited relational understanding and rarely capture spatial weighted graph information. Frontier multimodal models also make basic errors. They miscon components, identify the wrong kinetic elements, or misunderstand spatial relations. Even one incorrect connection can invalidate the resulting circuit graph. OmniScan addresses this gap using diverse real-world schematic designs rather than simplified circuit examples. Its rich annotations connect symbols, pins, text, electrical connectivity, and spatial relations within one unified representation. This supports comprehensive and reproducible evaluation from fine-grained visual grounding to complete netlist graph reasoning and agentic visual search. We collect open source industrial EDA designs and process their source files using our rendering and geometric engine. This automatically aligns the symbol, pins, text, and nets with the render images, producing detailed annotation without manually labeling every object. Our classical baseline detects symbol, pins, text, wires, junctions, and labels. It then groups pins with symbols and nets, merge local and global net labels, and construct the final netlist graph. We also evaluate a React-based agent. Instead of examining the full high-resolution image only once, the model repeatedly crops and zooms into relevant regions. It gathers local evidence before predicting symbol names, pin labels, net names, and connectivity. The end-to-end result reveals a clear gap between recognizing individual elements and understanding the complete circuit. Multimodal models can identify many visible components, but frequently miss small pins, associate label incorrectly, or introduce error while tracing connections. As a result, good local recognition does not necessarily produce an accurate netlist graph. Global topology remains the central bottleneck. Performance also drops as schematics become denser. Once an image contains more than 80 words, detection F1 falls below 50%. Real-world complexity therefore remains a major challenge. The agentic results are more encouraging, providing accurate localization and interactive viewport control substantially improves fine-grained recognition, especially for small pin and pad text. This shows that deciding whether to look is a critical part of schematics understanding. Most accuracy gains occur during the first few crop and refine steps, and then begin to saturate. Local visual search helps recognition, but it still does not fully solve global connectivity. Future systems must combine effective visual exploration with consistent graph reasoning. In summary, OmniScan provides a realistic benchmark for structured schematic reasoning. Our results show that current models can recognize parts of a circuit, but not yet reconstruct complete and reliable netlist graphs. We hope OmniScan supports future multimodal agent or engineering design. Thank you.